So shall we start the workshop? So yeah.
Just a second, we will start the recording. Oh, it's already started, yeah?
Okay, so I start. So welcome to our visual workshop on Python for satellite data processing and visualization. My name is Yongqing Chen. I'm the technical coordinator for infrastructure at the W Regional Office for Asia and the Southwest Pacific. It's my great honor to moderate this workshop. To underscore the significance of this workshop, it's my privilege to invite Mr. Ben Churchill, Director of the W Regional Office for Asia and the South Pacific, to deliver the welcome address on behalf of W Secretariat. Over to you, Ben.
Thank you very much, Yongqing. Dear colleagues, distinguished speakers and participants, good morning, good afternoon, good evening to all of you joining in from different time zones today. As Yongqing mentioned, but just to repeat, my name is Ben Churchill, and I'm the Director of the World Meteorological Organization's Regional Office for Asia and the Southwest Pacific. On behalf of Professor Celeste Saulo, the Secretary General of the WMO, it is my pleasure and it's my privilege also to welcome you to this virtual workshop on Python for satellite data processing and visualization. Before I start, I just want to actually take a moment to pause and reflect on the significant impacts of recent significant weather events across our regions, Southwest Pacific and Asia, from the Philippines to Vietnam, Thailand, Indonesia, Malaysia, and of course, Sri Lanka, with many lives lost, sadly, and many more lives disrupted through displacements and economic damage and so on. So I just want to appreciate all the work of the National Meteorological Hydrological Services trying to minimize the losses, but also for those that are on this call that might have been impacted or know people in the community impacted. So back to the opening remarks. We're delighted to bring together the experts from across the Asia and Southwest Pacific regions, united by our shared commitment to advancing the use of meteorological data for better services. This workshop was designed in response to the strong interest expressed during the 14th Asia Oceania Meteorological Satellite Users Conference, AIMSUC 14, held in New Delhi for the first time in India, which was last December. Many of the participants at that meeting highlighted the need for practical training in Python, which is, as you know, a versatile and increasingly essential tool for satellite data processing, visualization, and integration into operational workflows. Enhancing the use of satellite data is not only central to WMO's implementation of the United Nations Early Warnings for All initiative, but it's also a top priority for both the Asia and the Southwest Pacific regions. At the 78th session of the WMO Executive Council held in 2024, a resolution titled Priority Activities Contributing to the Early Warnings for All initiative was adopted. It tasked the regional associations with leading gap analyses of satellite products against early warning service needs and also developing implementation plans. Building on this, the Regional Association 2 and the Regional Association 5 adopted operational plans during their sessions in April and September 2025, respectively, outlining concrete measures to strengthen the application of satellite products. So today's workshop is a concrete step towards implementing those plans. We are honoured to have experts from the Hong Kong Observatory and also the Meteorological, Climatological and Geophysical Agency of Indonesia, BMKG, leading practical sessions on satellite data decoding, the SatAid Python package, aviation meteorological applications, and AI-assisted Python techniques. These topics were selected to address real-world challenges and to equip you with practical skills that can be applied immediately in your work. Your active engagement through questions, discussions, and shared experiences will be pivotal to making this workshop useful for you. So we hope that the knowledge gained will strengthen your ability to leverage satellite data for improved weather forecasting, climate monitoring, and disaster risk reduction. Beyond this event, we recognise the need to establish satellite application communities of practice across our regions. Such communities will serve as collaborative platforms for continuous learning, knowledge exchange, and innovation, ensuring that the skills and insights gained today are sustained, but also expanded. By working together, we can accelerate the integration of satellite data into operational services and strengthen our collective capacity to deliver timely and accurate early warnings. WMO remains steadfast in its mission to foster collaboration and build technical capacity across our regions. This workshop reflects our commitment to science for action, which is our phrase for the 75th year of WMO's establishment, transforming scientific knowledge into practical solutions that benefit communities. We encourage you to make the most of this opportunity to connect with fellow professionals, exchange ideas, and carry forward the knowledge gained to drive innovation in your respective fields. So, colleagues, presenters, participants, friends, thank you so much for joining us today and setting aside time for this important workshop. Let's make this an engaging and productive experience that strengthens our operational capabilities. With those words, I thank you very much for the opportunity to share some insights and some thoughts to kick off today's workshop, and I wish you all the very best. Thank you, everyone, and back to you, Yongqing. Thank you.
Thank you, Ben, for your inspiring and insightful remarks. What also, as mentioned, we also would like to express our gratitude to our key partners, Hong Kong Observatory and Meteorology, Climatology and Geophysical Agency of Indonesia, BMKG, whose experts have generously shared their time and knowledge to craft these tailored programs. For your reference, today's workshop runs from 1:30 a.m. to 4:30 a.m. UTC, 3 hours. We have a structured yet practical agenda ahead, covering everything from satellite data decoding to AI-assisted Python application. Please switch off your microphones during the presentation, and please type your questions in the Zoom chat box. We have reserved sometimes for Q&A at the end of the workshop. Now, let's kick off our first session, satellite data over the Asian Pacific region, decoding and product generation, developed by expert from Hong Kong Observatory. Please join me. Welcome Dr. Alan W.H. Tang. Over to you, Dr. Tang.
Thank you, Yongqing. So, yes, can you see the screen, the PowerPoint mode right now?
No, it's coming. Yes, we can see.
Great. Let's start my presentation then. Good morning, everyone. So, good morning from HKO here, and so I'm going to share a half-hour session and just conceptual from the conceptual perspective, because I know that you want to learn how to use the Python to decode the satellite data. So I guess at the beginning points you got the raw data somewhere for the satellite data, but we need the concept first to how to understand this raw data. Then you can use the Python and other AI to do the rest. For example, image generation and blah blah blah. So at my half-hour session, I will give a very introduction on how to understand the raw data. And this is my outline. And first of all, I will introduce the concept of the full disk, and because actually the satellite is just a camera and taking a full disk picture of the Earth and then invite it into maybe a 1,000 by 1,000 pixel image, and then you make the processing to make it in Mercator projection and other projection, and then as you like. And also we convert the variable into a physical variable and during the processing. And also finally we can do the imagery generation. And actually, in the last session of this workshop, and my colleagues will be going to share the existence from AI, and it actually the AI can make everything fast than your previous thing. And so she will introduce you how to use the AI with Python as well. So first of all, as I said, a satellite is just a camera and maybe just 55,000 kilometers above the Earth's surface and taking a picture. And for example, here it is the footage from Himalayan and taking the picture over the Pacific region and also the Asia, Australia region. But actually, it's not exactly half this area of the whole Earth, because we have some boundary around 81 degrees here because of the tangent line you can see here. So actually, if you do the raw data transformation, if you make it to around 90 degree to minus 19 degree, actually there's some region you cannot see. And so if you do the direct transformation on the raw data, for example, here, you can see there is some boundary here. It is the physical boundary related to the tangent line on the previous session. And for this region, you can see the boundary here, but if you open some the raw data with some software, you can see outside the physical boundary, you can see some data here, but actually it is not the correct one because it's just a reflection on this boundary. So keep in mind on this. So you know there is some physical boundary on this raw data. So in the post-processing, during the post-processing, you need to confine your image within this physical boundary to avoid some false information on your image. So personally, I will set the following boundary as following boundary for the latitude and also the longitude. For example, I will choose for geostation. Actually, in my talks, I was just focusing on the geostationary satellite. And for example, if we look at the latitude region, I was just focusing from 61 south to 61 north degree area, and also to because I don't want to see the most distorted data on the edge. So we are just focusing on this area. And for the longitude, I would choose 70 degree plus or minus from the satellite points. For example, if I use the Fengyun 4B satellite, then I will just do the mathematics and choose the boundary on this region. And actually, in this region, we have several geostationary satellites, and for example, JMA Himalayan Ace Online, and also Fengyun 4B from CMA, and also some GK2A from KMA as well. And also for the other region, for example, European region and also American region, we have some MTG in latest generation satellite, or also the Ghost series satellite. And actually some newer satellite, the data format will share in some so-called NC file structure in common, but I will introduce later. And for Himalayan Ace Online, actually the raw data we are obtaining from currently we are obtaining the raw data for Himalayan 9 from Himalayan Cloud, and it is in a binary DAT format, and so call the name Himalayan standard data. And in that case, and the full disk image will be divided into a 10 segment for each channel. So for example, Himalayan Ace Online has 16 channel in total, some infrared, so some visible. So in just one timestamp, you can get 160 segment for just one timestamp. And for example, in the example below, we can see for the band 13, for the infrared channel, we can see just one timestamp, we can see 10 segment data in DAT format. And here the S01, 02 describe the each segment. And the concepts of that Himalayan data storage will be looking like this. And segment, for example, 1, 2, 3, 4, 5. I don't remember the order, but the concept is in this demonstration. But because it is a binary final, so actually you have to use some you need to know how the Himalayan 8 or 9 store the information in this binary file. So it's important for you to get the user guide from JMA, and it's the link, and it will describe the whole structure of this binary file. But actually, I'm not going to talk this format in my presentation. And also, if you want to do the conversion from the DAT format into a familiar format, for example, NC file or some other Himalayan cast formats, actually JMA is providing some package on the web page, and then you can call the package and then do the conversion as well. But actually, in my talk, I will share the experience from GK2A, Fengyun 4B, and also Go series satellite, because the raw data is very common in structure, I guess, because once you understand one of the satellite data, then it's easy to do the remaining 2 satellite as well. And actually, they are providing the raw data in NC format or HDF format, if I remember correctly. And the principle is that the satellite imagery is just a camera. It's as I said, it's taking picture of the full this picture of the Earth, and maybe just 5,000 pixel by 5,000 pixel, just just ordinary image on your phone or your computer. But how the raw data store the information, and actually, as I said, it's for example, 5,000 by 5,000 pixel, and it is a table form. And depending on satellite, maybe some visible channel will have a higher pixel value on one edge, and maybe 100 or no, not 100, maybe 10,000 as well. I don't know. But the key point is the pixel value here in this particular pixel will store the measurement information, or so, for example, the brightness temperature, for example, the albedo, the reflectance, but not direct storage of that value. It will be coded in some integer value, as we call pixel value. And then once we want to handle this raw data, we need the conversion method to go from this coded data back to the physical variable. So in my following session, I will introduce 2 important conversion. One is from the pixel value here, for example, 1, 2, 3, 4, 5, and back to a physical variable, brightness temperature or albedo variable. And second, I will teach you how to find out the location of this particular pixel, because we just have IJ index here for the 1 pixel, but in order to make it useful for example, image generation or satellite products generation, you need to know the location of this observation as well. So I will introduce later on the second conversion for that pixel location. And first of all, it is recommended to use the Panoply software, and it is from NASA. And because once you download the software, you can quickly to preview the raw data and also check the parameter and also metadata. It is also okay to use Python package to do so, but I think the user friendly interface provided by Panoply will help you to do this checking quickly. For example, I just grab the GK2A raw data from this timestamp, and then I open it up with a Panoply. We can see a lot of variable, and then I can check quickly that there is some parameter called image pixel value here, because it's a 2D file, and I just select this parameter and also double click here, and I can already feel the image here. And as you can see, there's some cloud structure here and also Australia landmark here. And actually, you have success in a halfway already, because you have know what parameter you need to use, and also you will also already know the orientation, and the rest is do the previously mentioned the conversion formula from this data value back to the physical value and also the location. And so I will firstly sharing the first conversion from the pixel value to the physical value. Yes, and that's the first part here, the highlighted in red here. So if you open the metadata of this GK2A file, you can see a metadata called a number of value bit per pixel. Actually, we can see around 8,000 number for this particular file, and actually it could vary amongst various observational channel, and also even different satellite have different number. But you need to bear in mind that there's some range for this physical information. And for example, in this GK2A file, we can see it will store into a pixel value from 0 to over 8,000. But once you read the file, you can just see the 0 or 1 or 2 or maybe 7,000 value, but you don't know actually what is the corresponding brightness temperature. So you need to check the menu from, for example, if you are looking at GK2A, then you download the menu from the KMA webpage. For example, here it is the number 16 document from the KMA website, and then you can download the conversion table. And this is a Excel file, and in which you can see some conversion formula. And from here, this is the first formula. I'm talking about the IR channel, for example, and you can see the first conversion equation from the count to the radians. But during the conversion, you need the parameter, the coefficient gain, and also offsets. And actually, it's already provided in the Excel file and also metadata in the raw data. I will show you in maybe the next 1 or 2 slides. And it is the first formula you use, and then you can got the radians, and then you just use the second formula to convert it further into a effective final temperature, and then finally use another coefficient C0, C1, and C2 to further convert into a brightness temperature. So once you do this simple mathematics substitution, and then you can go from data value and 0 to radians here, or effective brightness temperature, and finally you got the brightness temperature here. And actually this lookup table is also provided in the same Excel, but if you want to do it by yourself, and then you just use this equation, and then you fit the parameter here, and then you can do reproduce this lookup table, and then you can already have the conversion formula from the data, the pixel value to the physical value, the brightness temperature. And so if you may think that the Excel is static, so there could be some update on the parameter, and maybe 1 year or 2 years later for the instrument. So if you want to make it very accurate, then you want to check the parameter every time you do the conversions. Then actually you can check the metadata, and it already store the same information. For example, the coefficient C0, C1, and C2, and so the gain and offset, you can check it every time here and use the algebraic equation and do the conversion again. Yes. And actually, I just talk about the IR channel conversion, but it is similar for the visible channel, and just use another set of the equation to do so. And it's also already explained in the KMA menu. And similarly, for Dongyun 4B satellite, it is from the CMA, and you open the raw data, which is in a HDF format, and you can see Australia here again. And it's stored the information in similar structure. We can see the data here, and also some calibration parameter here. And the data value for this situation, and we have around 4,000 valid pixel for this particular channel. I think it's also a IR 10 around 10 to 11 micron channel here. And then similarly, you find a appropriate lookup table to do the conversion for you, and then you can go from the data value to a physical variable brightness temperature, and that's the results. And actually, Fengyun 4B is even providing the lookup table on the parameters called calibration in the same file. Once, for example, for the channel 13, then you click the calibration table, and then I goes from I can display I can see the conversion table here on the right hand side, or graphically we can see this conversion table here. And actually it is just a lookup table and showing you how to convert from a pixel value, for example 2730 to a physical variable, the brightness temperature. It is the answer. And also similarly for the visible channel, for example, channel 1 and channel 2 is another, if you click the variable, you can see another mapping, and it is the lookup table for that's another channel. But actually, if you want to do the conversion by yourself, you can use the formula as well. And it's the information you need can be found in this calibration coefficient. But for the formula, then you need to check the manual produced by CMA, the NSMC here. But unfortunately, the manual only provided in Chinese, and so you if you find the web page and click on the Chinese version, then you can see the PDF here. But if you're looking in the English version, then you cannot find this PDF. But I just show you the key points here, and from the PDF, the section 3, it is introducing the conversion method. And besides the lookup table, we can also do the conversion formula, and actually it is the conversion formula here. And for the reflectance, and also the radiance, and also another parameter called the top of atmosphere reflectance here. And it is for the visible channel. And maybe there you need to check another parameter in the metadata, and also another GEO document to grab another physical variable for this equation. But for the IR channel, and there's also there are two methods as well. One is the lookup table, as I mentioned, the calibration channel, the lookup table. And other one is to use the coefficient and scale and offset, and using this formula to use this formula to do the conversion. But actually the two parameter difference. One is the brightness temperature, and other one here, using the scale and offset coefficient, you can got the radiance parameter instead of the brightness temperature, and depends on what you need. And actually for my personal use, most of the time I just use the brightness temperature in my image drawing. So I'm okay to just using the lookup table. And for interest, if you are searching the decode information for a European or American satellite, for example, the MTG, the Meteosat 12, or also the GOES 18 or 19, actually you just do the same thing. You grab the user guide and see how they store the data, and then you know how to convert the data back from the data value to a physical value. And so I just placed the link here if you have interest on this satellite imager. And previously I have discussed how I convert the pixel value to the physical variable. But another problem is I don't know where the location the pixel is. So I have done for this data value to the physical variable, but I also need to convert the IJ index to a lat long latitude and longitude pair here. So how to do so? And actually, to do such conversion, you need the information below. The first is, of course, is the Earth model, because you need the size of the Earth behind the data storage, and the concept and constructed by the, for example, KMA, CMA, what Earth model they are using. So I need the model, for example, the radius of the Earth, and also the resolution of this file. For example, infrared has lower resolution, but for visible channel, we have you may have over 10,000 pixels on one edge. And also finally, just the longitude of the satellite, because in some sense you need to add a offset for the resultant longitude to get the correct observational location. And for example, here, as I said, if you look at the full disk image, you're just focusing on one of the line. Actually, you see a lot of pixels here. And for each pixel, maybe I'm using the Gold Satellite 2K resolution for this demonstration. The value for this value is just particularly for this file, but the concept is similar. You can see for each pixel, the width of each pixel is around 56 micron radian in viewing angle. And also you can check on the edge of this line, you can check the viewing angle of this pixel at the edge of this pixel. But for this edge pixel, you can see a center of this edge pixel here. And actually there is some little difference in the viewing angle, and then you need to know what location you are looking at. But the rest is do the conversion. And actually, it is good to see Gold Satellite data, although it is not looking in the Asia region, but because the user guide is long and also the explanation is good. So I'm quite enjoy reading this user guide to understand the lat long conversion from the picture and also the example and also the formula here. But in short, they are providing the conversion formula from the previously mentioned viewing angle, X or Y, to the resultant latitude and longitude value. And actually, once you have this formula, you can do the inverse, and then you can got the latitude, once you have the latitude and longitude on your hand, then you can convert it into a viewing angle by the inverse formula. And so in short, once you have a latitude or longitude, you want to see this particular location, and then you can do the calculation to get the viewing angle XY in radian, the angle value in radian, and then you can know the closest pixel it is corresponding to. And here, for example, if you know that I want to see a specific viewing angle at 0.123456, then you do the calculation. You can find that the closest pixel index will be 4917 here, and that's a check variable. It is very close to it is nearest pixel to your original question. And actually, some organization has provided such conversion in a package or a library here for your use. For example, KMA has provided a Python package here. I just copied this from the KMA KMA manual, and also it is also available to download as a Python package from the web page. And actually, you can see that's just similar information you need to know. And the Earth model here is already written in a code font and in the blue box here. And also, you need to define the resolution of your file, and so it is already determined by this green box here. And finally, you need to know where the satellite is, where the observation is made. So it's already in the red box here. And then this library, you need to say I want what line and column I'm interested, then and using this conversion formula, it will reproduce the latitude and longitude in a result for your use. So actually, it is similar for the Fengyun 4B, but just you need to change the parameter and also Earth model a little bit, and so that's why at the first beginning point, you need to get the data menu for the conversion. And so it is the same library, but the inverse part, and you can convert the latitude and longitude back to the line and column in the later parts of the same Python package from KMA. So finally, we have done the conversion from the data value to physical variable on the first part, and now I also teach you how to go from the pixel index ij to the latitude and longitude here. So now you can draw the grid line to write down the grid line here, and then you can locate the cloud or object on this imagery. But unfortunately, it will be still in a full-disk format, so the spacing between latitude and longitude will not be uniform. So finally, I will to facilitate the further image drawing and product drawing, then we need to reproject the data from the previous non-uniform spacing to a uniform spacing. And actually, it's not quite difficult. For example, you just firstly create a table, and it is maybe 3,000 by 3,000 pixel, depending on the resolution or spacing of the longitude and also the latitude you want. For example, here I choose 0.05 degree spacing for longitude or latitude, and then I want to do the extension here 140 for longitude and also another value for the latitude. Then you can already know what the size of this empty table is, and then you already know the lat long here because you defined it by a uniform spacing, and then use the previous conversion formula. You know the corresponding column and line pixel in the very raw data. I mean the NC file from the cloud. I mean the IJ value, the full disk raw data, and then you know the location, the pixel, and then you grab the value from that pixel. For example, the data value or the already converted physical variable. For example, the brightness temperature from that raw data pixel, and then write down on your this empty table here, and then you do every pixel with similar things. Then you can create you have already reprojected the data from the full disk data in a uniform spacing latitude and longitude data. So for example here, and I have already converted the GK2A visible channel from the previous full disk data in the uniform space raw data. That's why, but within the physical boundary, so you cannot see the mirror and also reflectance on this file because I don't have interest on that area. Then you can see that, and you have the image here, but I need to check whether the conversion is correct or not. Then I can use a naive but fast way to do so. For example, you just check the lemma. You open the image to see whether the coastline of Australia fits the image here. And also, but for the brightness temperature and other way, I will check the correctness of that converted brightness temperature is by using the DeWolf image because it's discrete in color. So we're just comparing two images to see whether you have converted brightness temperature correctly. And actually, similarly for the regional scan, but I'm not going to say a lot here, but same concept, but regional similar concept, but regional is just focusing on some particular line to another particular line and also particular column to another column. So just a similar conversion, but you need to be careful on the whether it is start from 0 or 100 to another point. So yes, similarly, I do the data conversion and also reprojection from the raw data here to another data table with a uniform space ledlon, and then you draw the image, then you can see a reprojected satellite data or image on this right-hand side. So finally, I just show you some conceptual perspective on how to do the portrait and imagery generation from the previously generated raw data. So once you have the uniform gridded latitude and longitude data, and also in a brightness temperature value, then the remaining thing is to define a color code, color transformation. For example, you know, maybe we have a grayscale 0 to 255, and 0 is referring to the black color, and also the 255 is referring to the white color. And then you define the interested parts of brightness temperature. For example, in HKO, I use 180 for the white color, and also 310 for the black color to define the boundary. And then you use, once you define the red line here, it is depending on what you want and which part you are interested in, and it's up to you. But I use this at HKO here, and then you do you just make it the digit into a color, and then you can get the page satellite image here. And similarly for the visible channel, and it's albedo from 0 to 1, from black color to white color, and then you can draw another visible channel here. And then you combine previously I just used one channel. It is a grayscale picture, a black white picture, monochrome picture if you are a photographer. But if you want to see a colored image, then you can define your red component, green component, and blue component just from the red observation channel and green and also blue channel, and then to draw the image together, and then you can get a true color. But maybe you need to do some gamma adjustment to enhance the contrast. And here I'm showing you some timestamp with a solar eclipse here. And also similarly for other RGB channel, and it is the HKO false color we are using, and you can discriminate the low color to the convective color from this yellow to white color here. And also even you can draw the SO2 RGB. For example, is the 1 or 2 weeks ago, some eruption from the Africa Hale Gubbi volcanoes. The SO2 plume is drifting along with the westerly upper air westerly wind and affecting the northern parts of India, and also later on to affect the central China and also the south of Japan here. And finally, some fire temperature RGB, you can also see clearly where the hotspot is, and also the eruption of volcano as well. So finally, I just make the summary here. I have teach you the following things. One is the concept of the full disk, because it's the very common starting point of the raw data, and then the second or third or fourth part is the conversion formula, because you need to convert the pixel value to a physical variable, the location from a column line to a latitude and longitude information, and then for your convenience, you can do some reprojection before making the portraits and imagery. And that's all for my part. And maybe on close to CO3 or CO4 UTC, and my assistant will introduce you how to use AI on the with the how to applying Python with AI. And yes, please stay. And that's all for my part. Thank you very much.
Thank you, Dr. Tao, for your comprehensive and insightful introduction. Once again, if you have questions, please put your questions in the chat. Presenters will take your questions at the end of this workshop. So next, we will move from theoretical fundamentals to a hands-on tools that will become a step in your workflow, the Satellite Python package. This 60-minute sessions will be led by expert from BMKG. It's my pleasure to introduce Dr. Appon Supriyanna, the team leader from BMKG. Please join me to welcome Mr. Supriyanna. Over to you.
Thank you. I will share screen. Can you see my screen?
Yes, you can see.
Okay, I will start. Hello, everyone. Thank you for joining this session. My name is Alphonse Supriyanna from BMKG Indonesia. In this part, I'm going to introduce the Satellite Python package. It is a small but important tool to help us bring Satellite data into Python workflow. This is first time I am presenting for the package, so I hope today give you a good understanding of how using this package and how to start it. Okay, here is what we are going to cover. We will start with a quickly introduction to Satellite, then look at why Satellite data is still important and where we can obtain it. After that, we will explain the motivation behind developing the Python package, followed by its main feature. Then we will continue with a hands-on session in Google Colab, and finally look at what we plan to develop next. Satellite stand for Satellite Animation and Interactive Diagnosis. It is a visualization tool that helps user, especially weather forecaster, view and analyze meteorological information. Satellite data and application are provided by the Japan Meteorology Agency, and thanks to GMA for making this resource available. As you can see from this example on the slide, Satellite can overlay different dataset, display animation, and combine satellite data with NWP or observation data. This makes it very helpful monitoring real-time weather condition. However, Satellite is mainly a graphical tool, and it uses a special binary data format. This format work well within the software, but it also introduces some limitation when used outside the Satellite environment. Why use satellite data? Yeah, satellite data still has several advantages. One of biggest is that it is fully supported by satellite application, which make it's very easy for forecaster to analyze and visualize satellite information. And another advantage is the data file are much smaller because they are compressed and regional specific. For example, for Indonesia area, one satellite file is about 12 megabytes per channel per time, while the equivalent data in NetCDF format can be around 24 megabyte. This make satellite data much more efficient for long-term storage. Satellite data also available in real time through the Japan Meteorology Agency WIS portals, which many agencies depend on. And the case of BMKG, we have archived satellite data since 2015, giving us a long historical data set that is ready to be used for research, training, and another analysis. Satellite format can be come from a few different sources. If your agency use Himawari Cloud or Himawari Cache, the raw Himawari data arrive in HSD format, and this usually need to be converted into satellite format locally. However, if you access the data through the WIS portal, the file are already provided directly in satellite format. This is very convenient because the data is ready to use immediately in satellite application. So depending on your system setup, you may receive raw SSD data that requires conversion, or you may receive data is already in satellite format. Although the satellite application is very helpful for visual analysis, it does have limitation. For example, satellite application not designed for automation or large-scale data processing. Like this, the binary format cannot be opened directly in Python or GIS or scientific analysis tool. And some user only need a smaller area, but the full dataset is much larger than they need. And also, satellite provide only limited number of default product. So if we want to generate additional derived product, like convection area detection, we need more flexibility. As the solution, we developed the satellite Python package. It removes many limitations of the conversion satellite software. With this packet, we can read the original satellite data in Z file. We can say Z file directly in Python. So no manual conversion needed. It also provides quick visualization using Matplotlib or Cartopy. And the data can be exported to common format like NetCDF, GeoTIFF, and XRI. So it integrated easily with other tools. And if we only need to specific area, we can subset or crop the area region directly in Python, making files smaller and the analysis more efficient. Yeah, the satellite Python packet is a Python library that allow us to work with satellite data directly in Python. The idea is simple. The satellite software is excellent for manual visualization, but it is not designed for automation. So this Python packet fill gap by enabling scripting, processing, analyzing, and conversion. And for the installing the packet is straightforward because it's already available in pypy.com. You can open pypy.com and type satellite. And for the install, just using pip install satellite in your terminal or command prompt. We can later in the demo, we will run this command inside Google Colab. Next is let's take a look at the main feature in satellite Python package. The first is the package can directly read satellite binary file. There is no needed any manual conversion, just load the Z file and Python immediately provide both the data and its metadata. Second, the package offer flexibility visualization option. We can plot the satellite image in grayscale, add cartopy overlay like coastline, grid line, or apply custom color map like rainbow, terrain, jet, and others. This make it very easy to explore and interpret the data visually. The third is packet allow us to extract pixel value at the specific coordinate using longitude and latitude. So if we need the temperature or lepectan at the particular latitude and longitude, we can retrieve with a single command. For the package support spatial subsetting, you can crop the dataset to smaller region like Indonesia domain or Borneo Island, making the file lighter and processing faster. Fifth, it included automatic plot export. Any visualization we can produce can save directly as PNG with one simple function. And finally, the package support exporting data to widely used scientific format like NetCDF, GeoTIFF, and XRI to ensure compatibility with many other tools, platform, and workflow. Overall, this feature make the satellite Python package highly practical, not only for research, but also for operational methodology. Okay, we will now switch to hands-on. Please open Google Colab because we will run all example there. We will clone the GitHub repository that contain example file, then install satellite package directly in pypy.com. Okay. First, you need to open the Google Colab. Okay. I will copy the GitHub link in the chat box. Where is the chat box? Okay. You can copy the GitHub link in the Zoom chat box and copy the link, and after that paste the link in here. Yeah, once you press the enter, the notebook will open directly in Google Colab and you can start running in the code. I will practically in slowly. Yeah, sorry. Yeah, before we begin working with satellite data, we will start with the environment setup. I will emit. Oh, sorry, slide. I think it's better. First, resetting the path to content. This one. To make sure cloning always happen in the correct location and avoid creating nested folder. And after that, for the RM, this is in the cell we first remove anything existing copy or of the repository using RM. This step ensure the notebook can be run repeatedly without error, especially when participants restart the runtime or rerun all cell. And the next is this one. We using exclamation git clone. After the running this, you will see the new folder on the left panel. And finally, we change into the folder using satellite example. This is tell collab to switch the working directory to new clone repository. So all the file we load or script we execute will reference the correct location. Run the script. Just because I open many session. Okay, to make sure, run again. Okay, it's successfully. First, we go to satellite packets page on PyPy. Okay, this one. As you can see, the current version is 1.00, which means this is first official release. I actually started developing the package about 3 or 4 months ago, beginning with the beta version. Okay, we continue to this one. Okay, the first we need to install the package satellite using exclamation pip install satellite. Just using this script, we can install satellite Python package. And after that, for the supporting package installation, we need to install Cartopy and Raster.io. In this part of cell, we install several supporting packages that are required for geospatial plotting and file handling. And Cartopy is used for map projection, adding geographical feature like coastline and gridline. Meanwhile, Raster.io help with reading and writing geospatial raster format, which become useful when exporting data to format like GeoTIFF. Now, I think successfully. Okay. Now that our environment is ready, let's move to load the satellite data and exploring its structure. Okay. This section introduces the process of loading a satellite file and inspecting its metadata. We will work with sample file from repository. Close script. We can see at the left side, this is the file containing the data folder and satellite IPyNB file. You can open the data and see the sample data. I put the several file. The first I'm using from Himawari Cloud, and the second from Himawari Cache, and the last from Himawari Wish, is GMA Wish portal. Now let's import the package using import satellite as set. In this cell, we import the satellite module or package and specify the path to sample file we want to read. For example, we want to read the infrared band, this one, B13, area in Indonesia. And the letter we can change and using the visible band. The function read satellite, this one, load the binary or Z file into satellite array object. And when the call satellite description, which print the key metadata like channel, timestamp, projection, array, dimension. Okay. We run. Okay. It's loaded. You can see description about file. This is timestamp. The name of satellite Himawari 9, and for the channel or band, IR is infrared, and dimension of file and unit because it is brightness temperature using Celsius, and longitude and latitude refer the area of the data. Okay. After successfully loading the data, our next step is visualize the image so we can get an initial look at the content. Okay, this one. We can visualize the data directly using the Python plot. You can the simple way to open the data. In the cell, we use a matplotlib imshow function to display satellite data in grayscale. It's provide a quick and simple way to confirm that the data has loaded and correctly, and to get initial understanding of the brightness temperature or reflectance distribution. As you can see on the grayscale plot, top left show this one, the satellite name, in this example Himawari 9, and on the top right we have the observation time from satellite. This is just for example. And on the right side we see the color bar and its unit. It is brightness temperature, and the unit is Celsius. If we load the visible channel, the color bar represent reflectance. We can run again for the visible band. Run again in this code. After that, run again. Don't forget for the run to plot, just data.plot. Just it, you can see the result. This one, reflectance for value. Okay, we continue. Next, we enhance the plot by adding geographical context using Cartopy. Using the syntax just data.plot and add the Cartopy equal true. In this cell, we create the Cartopy figure and use the data built-in georeferencing to display with the proper map coordinate. We add coastline, grid line, and extend the focus on the region interest. Okay, run the script. This produce meaningful geospatial visualization of the satellite image because it's using the visible band. No significant change from the last. We can back to the visible band. This plot, after that, this Cartopy. Okay, after that, run again, and we can using different color map to enhance interpretation. In this cell, repeat the plotting process but apply different color map like this anchor, jet, terrain, and etc. For example, I change for the jet. Yeah, like this. You can refer to the complete list of available color map in our official Matplotlib documentation. This is several color bar from documentation of Matplotlib. You can change, just type, for example, you want to binary, spring, summer, and others. I'm also put some modification color bar. For example, I put for the EH. This is a custom color bar we using in BMKG or like this. Just if you want, so if you want to plot like this image, you just using 3 line to plot this. Okay, the next is save plot. Okay. This section cover how to save generate plot as image file. You can save them using the default file name provided by the function, or specific a custom file name if you prefer. For example, I'm using default name, just using data dot save figure, and using the, don't forget to using Cartopy equal true, and run the script, and the file saving to location. We can see in the folder. Okay, this one. Just double click to open. You can see this is the result of the saving file. Okay, the save PNG function allow to export any visualization directly to image file. It is useful for documentation or sharing result with your colleagues. By specifying the name file, the package automatically save the current figure into working directory, and for the make it easy to keep record the plot without needing manually. And you can type the name of a plot. In this case, I'm using my plot.png. You can run the script and save it to my plot.png. We can check the letter. Okay, the next is subset region. It is subset the data for the specific region. Sometimes we need to need a smaller region instead the full satellite image. We now demonstrate how to crop the data spatially. In this part, introduce selecting bounding box to subject the image. In this cell, we define the bounding box that cover the Borneo region and use the subset dot data dot cell to slicing the data. It is for the longitude, latitude, and this is for longitude. And we can describe the file using description function and run the script. As you can see, this is timestamp, but we focus the shape. This is a dimension of the data because the data are ready to crop, and longitude and latitude refer the value, this value, I mean. Okay, the next here we visualize the crop region using simple grayscale plot and this script. This allows us to confirm that the subsetting operational work correctly. You can see one, this Borneo area. Now that we have a smaller data set, so we can save it different format. The next is we focus on the extracting specific pixel value from dataset. In this cell, we demonstrate how to extract the data value at specific latitude and longitude. We begin by defining a simple point. In this case, at latitude and longitude. Latitude, refer this one, and for longitude, refer this one. The first method we use the default nearest neighbor selection. Here we using dot cell one. Dot cell function we find the closest pixel to request coordinate and return the value. And next we show the linear interpolation method. this one, linear interpolate method. This approach estimate the value by interpolating between surround pixel, which can give smoother and sometimes more accurate result, especially when the request point fall between grid cell. And this method requires SciPy to install by comparing to printed output. User can see how two different extraction method may produce slightly different value depending on the spatial resolution and location. And for example here, it is just little bit different, but in other case maybe quite different. And the other is convert to other format. This session demonstrate how to convert satellite data into other common geographical format like ANSI or GeoTIFF. These formats are widely used scientific workflow and make data easier to integrate with the other tool or analysis platform. The first is convert to other format, convert to NetCDF format. In this cell, we export the subset name is Borneo underscore box to NetCDF format using the dot to NetCDF function to underscore NetCDF function. Basically, I'm using the same syntax like XRI package. If we don't specific file name, the function automatically use the default name based on the dataset. Like this, exporting to NetCDF, blah blah blah, and .nc. It's mean NetCDF file. We can open the NetCDF file using another platform to ensure, like Panoply. Okay, and the next is convert to GeoTIFF format. You can check the output in the satellite example folder. After this, I put the name is customize satellite.tiff. This conversion make satellite data compatible with many external like XRI, Panoply, and GIS software like Quantum GIS. And the next is convert to XRI and use it feature. In this session, we look at how to convert satellite data into XRI data array. XRI is powerful library for working with labeled multidimensional data. By converting our satellite subset into XRI, we can easily select latitude, longitude range, calculate statistic, and create plot directly from the data. This is make the analysis more flexible and allow the dataset to smoothly into scientific workflow. Now look at how to conversion work to and explore of XRI feature. In this cell, we convert a Propit satellite dataset Borneo underscore box into XRI using dot to underscore XRI method this is a simple way. Refer from for the last syntax to X array, and after that we type for XR underscore data to open the data. This transformation at level dimension and coordinate information like latitude, longitude, and making the data set much easier to work with this file. Once the conversion is complete, we can use the XRI for full index, like indexing, slicing, statistics tools, and built-in plotting function. You can see this is description for the data. This is refer for the channel infrared. This is dimension of the data, and this value of the data. This is value of the latitude, and this is value for longitude. And the other attribute is unit and name of satellite. And the next is access data value. Like previous one, we can get the specific value. In this case, I'm using nearest method. Just run this cell. We can get the value for the specific area. In this case, 20 Celsius degree for infrared. Maybe we can change for the other value. And get the other value. Okay. And the next is calculate the mean value. In this cell, we calculate the mean value of the entire XRI using the .min function. XRI makes a statistical operation like this very straightforward because it's automatically apply the calculation across all grid points in the dataset. The result gives us a single representative value that reflect the general state of the data. And the other is adjust the slice to select value trains. Basically, the same syntax from the last script. We can run the script, but this is a specific area. Refer for the latitude and longitude. You can describe the data. And the next is simple plot. Yeah, XRI. We can use XRI to simple plot. Just the name of subset data and dot plot. We can put run this script and get the plot. And the next is creating a histogram of the data. In this cell, we generate a histogram of the data value using XRI plot histogram function. This allow us to quick see distribution of the pixel value across the entire dataset. Okay, I will go back to slide. Okay, this is the first release there are already several feature planned for the next version. The first is support for Himawari standard format. It is enable direct reading and visualization of the raw Himawari file. The second, integration with numerical weather prediction. It is compatible with GS model, global spectral model output for the comparative and blended analysis. And the next is support for the observation data. It's allow ingest and observation dataset distributed by WIS data portal, GMA data portal, sorry. And the next is RGB composite function. It is automate to generate of standard RGB imagery like true color, air mass, dust, and natural color, true color, and others. And the next is parallax correction function. It is implement geolocation adjustment for high cloud displacement correction. And the next is additional algorithm, specific algorithm. It is incorporate algorithms like rainfall estimation, convection initiation detection. And the next is machine learning or AI model integration. It is enable the use of machine learning and AI-based model for enhanced analysis and prediction. It is so this packet will continue to grow based on your needed or feedback. And the last, I will show you open the data. The first using for the GeoTIFF file. After we convert the satellite data to GeoTIFF, we can open the data using Quantum GIS. It is just make sure the workflow is work okay for the GeoTIFF. This one, satellite.tiff. I've download the data, satellite.tiff, and we can add the raster value. Yeah, this is satellite.tiff convert from satellite data. So we can operate to another function like overlay with other like shapefile, and maybe you want to generate some RGB and others. And the last is to ensure of the NC file. Okay, I will open the Panoply. Sorry, my Panoply. I cannot show the Panoply. I try again. Okay, just wait a moment. This is a Panoply application. We can open the file. This one. This is NC file. After that, we can see the description of the file. And after that, to open the file, just double click for the infrared parameter. And we can see this is Borneo area converted from satellite data. Okay, I think that's all from me. Thank you very much for your attention. I hope this session help you understand how to satellite data can now be used more flexible in Python. I look forward to your feedback as we can continue improving this package. Thank you.
Thank you, Paul, for the informative session. The demonstrations of real-world application in the Pacific region were particularly helpful. I am sure many participants are eager to test the packages themselves. Now, we have already seen some questions in the chat. I would like to invite Aaron and Apon to take this question for the next session. I would like to invite my colleague Julia to put these questions on the screen. Thank you, Julia. So I don't want to read every question because some questions already, Aaron already respond to some questions. I just want to invite Aaron to make elaborate on the questions and the answers. Later, other participants can understand. Thank you, Aaron. Over to you.
Yeah. So yes, I've already posted the answer to the question. I'm not sure whether I am okay to answer your question, but the key point is the once you have the NC file, maybe actually from level 2, you for example some cloud information. I understand that Fengyun 4B is providing similar level 2 products, and but the key point is how can we correctly decode the location of the file? For example, they are encoding the data in pixel I and J, and then the question, the remaining problem is to convert the pixel to a correct location. So that's why the previous the method I introduced in my presentation, the conversion formula, although I'm using the imagery, the level 1 imagery as an example, but actually the concept is also applicable to some level 2 products. And if you, the key point is you look the data structure in NC file, and also you grab the menu from the agency and to see how they encode the data. Then you do the similar thing with V, and then you can got the correct location. And yes, and other things for the Himawari 8 and 9, because I understand that they do not provide the exact NC file directly to the downstream user. They just have the HRIT format or the DAT formats, and also Alpon from BMKG just introduced you a package to handle it, to convert it into a NC file, and maybe his package is useful to do so. And of course, you can also download the converting package from JMA webpage as well to do so. Yeah, but and that's why GK2A and also Fengyun 4B I have introduced in my presentation work well, because they already deliver the NC data structure to the user already. So it's quite straightforward to understand the data structure. And yes, I think that's all for my part, and thank you.
I already have some explanation to the question and answers. I don't know if some participant would like to. Are you satisfied, or any further questions to the above questions or his explanations? If you have, you can raise your hand. If no, we can move to the question to Apple. So, Apple, floor is yours. Can you answer the questions on the screen?
Yeah, the question, what are the requirements for the Panoply? For Panoply, you can download for the with the NASA page website, and you can download depend on your operation system. For the requirement, you need to Java 12, I think. Yeah, Java 12. I think it's automatic when you open the Panoply, and after that, the link for the install Java 12, it's already open. And the next question, from the hands-on example of the satellite data in Python, the satellite imagery policy already example folder. Where did get the satellite image data reference? Do you mean describe about the satellite? Maybe you can open your mic. I want to need to classify your question. Okay. Where did we get the satellite data? For the satellite data, for the maybe if you from the National Agency for Meteorology, for example in BMKG, you can request the account for the satellite data. For example, WIS data portal. It is just 5 channel, but it is a basic channel to analysis or visualization satellite data. Okay, if I have more time, I will open the satellite data.
Yes, please.
Okay. Yeah, where is okay. This one. To be honest, to access the satellite data, you need to account for access the data. But this WIS portal very helpful to using the data. You can get the satellite data and for the NWP data and others like SST data. It is real-time data. You can check. This is, I think it's real-time data. 310 UTC, and for the open this data, you can just download, and after that change the path and using the satellite Python packets. Basically I'm already create the some script for the script. It is using for the connect to WIS account, but need to WIS account. After that, generate URL by datetime and download satellite data and plotting the satellite data. But it's not complete yet. Maybe in the next workshop, I will share how to download and how to plot the data So, and for the other level, for today it is just level 1. For level 3, we create the graph and animation like this, and we can run the script. Yeah, basically you can open or get the satellite data from GMA WIS portal. Thank you.
Okay,
Thank you, sir.
So let's move to the next session. At the end of this workshop, we still have chance to answer questions. So let's move to the next session. Next session focuses on high-stake practical application of satellite data. Aviation Meteorology Service. We are fortunate to have expert from HKO leading this discussion. Please welcome Dr. Dennis YLN to share her insight on the application of satellite observation for aviation meteorology service. Over to you, Dr. Dennis. Yes.
Thank you very much. I'll just start sharing my screen. Okay. So I hope the screen being shared and you'll be able to view it.
Yes.
Although I have mentioned it is for the aviation meteorological services, however, the I guess the whole code is actually very useful for public weather services as well in general. I'll be talking about how you can first connect to Colab with your Google account. And I'll use both data from JMA using the Hiramari 9 as well as the Fengyun 4B by CMA as well. So I'll actually go through the process of how you could download the data from JMA and how you could use their provided codes to translate the Hiramari 9 data into NetCDF. And then I'll talk about how to use the Python to actually work with the satellite data and output a GeoJSON. You can decide on different thresholds, different parameters that you have in the satellite data in order to output these GeoJSON, which highlighted the regions that you might be interested in. And it could also be feed into the downstream application for us. Sometimes we'll highlight the regions with very convective clouds identified by the, say, N13 with very low cloud top temperature and very low reflectivity temperature, and we'll be able to output that as a contour, which we'll be able to display at other platform for forecaster references. As mentioned, this is the Meteorological Satellite Center page by JMA itself. They do have data access, different links, so depends on your agency. You might be able to get it from Hiramari Cast or Hiramari Cloud. You need a specific account for NMHS for the Hiramari Cloud. They also provided the decoding information as well. So if you actually go into the Hiramari 8 or 9 data page, which is here, you can have a look at the general users who can download things from Hiramari Cast. These are the information that they will be able to get. For NMHS, they provide a bit more of the so-called level 2 data as well, as mentioned. They only have targeted area for the NetCDF format. For full disk, you have to work with the raw data. And they also have satellite wind data derived only for special users via different portal. Towards the very bottom bit, which Alpin already shown, this is the sample source code to read the Hiramari standard data provided by JMA. So you can make reference to that as well. And for today, I'll also talked about how this source code would be able to be incorporated into a Python script for you to read the raw data itself directly. For the Fengyun satellite, you can make reference to the National Satellite Met Center by CMA. And here are the different channels available on that. And as Alan has mentioned, some of the data or information was only provided in Chinese, but I guess you can easily translate that into English with the help from the AI. These are all the different channels available for the Fengyun 4B satellite imageries. This is one of the code that you can use in order to read the level 1 data as well. So I'll come back. So this is my Google Drive, and I'll go through in the Google Colab. So I'll just share the first one with you at the chat room as well. So if you want to, you can go through each of the steps together. Make sure you copy this Google Colab script into your own drive. So you'll need to sign into your Google account first. Okay, so I hope you can see this is what being opened. Personally, I like to mount the Google Colab into my Google Drive, as mentioned by Alpen in the video that has been sent earlier on. You'll be able to keep all your scripts in your Google Drive, so it won't get lost after the connections has been stopped for your free Colab account. In order to mount your Google Drive, you'll probably need to import this drive function from Google Colab. After you've run it, you'll be able to connect to your Google Drive. So this is what you need to do: connect to your own Google Drive. And you can run this screenshot, choose your own Google account in order to continue with using the Google Drive associated with the Colab notebook as well. You'll need to allow permission for Colab to use your Google Drive storage. Okay, so after you've done that, you can also work with a working folder within your Google Drive. Normally, the default would be your My Drive section. And in order to keep everything in one folder, I've actually provided the source code for you to make a new folder in your Google Drive. So you can have the sample satellite data as well as all these sample codes to be, or even the GeoJSON output all together in one folder in your Google Drive. So if you run this part, you'll be able to create a folder into your Google Drive. So after I've run this, you can go back to your Google Drive. If you go to my folder, you can see this 2025 Satellite to Aviation Met Service folder has been created. As mentioned, we'll need to use the JMA sample code. This is how you can get the sample code from the JMA link. As you can see here, it would have been downloaded as a zip file. Now you'll need to unzip it. So make sure the file has been downloaded, and you'll be able to make a directory to put all these sample code all together in a folder, and you can unzip it with this code shown in here. Okay. There are a few libraries that we'll need to use in order to generate the NetCDF needed. First of all, you can take a look if inside this sample code NetCDF version provided by JMA, if the script has been available in your folder. Okay. And then install the library first in order for you to use it within your Python scripts. These are the required library as mentioned within this JMA folder. It doesn't take too long for the installation. And after you've done that, you'll need to make the file, which is the hex2 netcdf script prepared by JMA. So they were written in C format. However, you could easily use that in the Google Colab environment. For this particular example, I have already prepared a zip data file for band 13 from Hiramari 9, as well as another level 1 dataset for Fengyun 4B. So here you can just download it via this link here. I've been sharing this particular zip file for the participants to download, for all of you guys to download. And because I want to keep things organized, I also provide the zip file being unzipped in here, as you can see. By unzipping this and unzipping the BZ2 files, you'll be able to get the list of DAT file, which are the raw binary file formats. As you can see here, this is the final unzipped version. As mentioned by Alan, they are being scanned at 10 different sections. So you can see this is band 13, and you'll be able to see the scan part 1, scan part 2, all the way to scan part 10. In order to convert the satellite data into your netcdf, this is the file that we make, which is also provided by JMA as mentioned. You need to fit in all these input file for the 10 sections of this band 13. You can choose the resolution of the output of your netcdf file. And for me, I've just used the raw resolutions, and I have picked a latitude and longitude for the region that starts from 50 east and longitude 90 east, and also latitude 50 north. And I have output it as a netcdf file. So this is how you can run the translation data from the binary DAT file into a netcdf file. They also mentioned the spatial resolution that you can use. They will interpolate those directly if needed. I think it takes a minute or so in order to get the full band to be read. Okay, here you are. So this is band 13 from Hiramari 9. These are some of the example data. So across the column here, you can see the longitude and latitude across the row here. You can quickly see the NC dumped, that the netcdf file is what you've been looking for. You see the variable as well as the attributes provided here. I hope this is useful in going through how the raw data file from the download as well as the translation into a netcdf. Okay, so we can move on to this part 2 to actually see how this netcdf could be done. So I'll just share the link as well. All these notes will be shared after the training, as I'm aware. So there's no rush to go through each of them at this stage. And because we're working with geospatial data, it would be great to load some of those packages. And as mentioned by Alvin as well, it would be good to have the data into X-array format, because it will make it a bit easier for you to slice the data as well as to find the thresholds that you will want to highlight the regions with, say, very low cloud top temperature and things like that. So here is how you can input all this file. The GeoPandas, the Shapely are used to output the GeoJSON for your later use. Matplotlib and Cartopy would be used for plotting. I'll also show how they could be used towards the very end of this script. You can have a view of the output of the GeoJSON overlaid on the raw band 13 reflectivity. Okay, so this is this shown or has been loaded. And again, I'll just double check I have mounted to the right drive. Just make sure I'm still staying connected to this Colab notebook. Okay. And as mentioned previously, I have already translate the DAT binary file into a netcdf file. So here I can load it directly as a netcdf. As you can see here, Xarray does have a open dataset function to read netcdf directly. And here you can quickly check if the data are in the right format. Because we're looking into the brightness temperature, the standard variable for it would be TBB. If you would like to read other variable, as mentioned in some of the question in the chat room, you can change the variable name as long as your netcdf has those variable. You'll be able to extract them as your working data set in here. So after you run it, reading in the sample, and then quickly check it could be read into your Python as an Xarray, as you can see here. So this is the data variable, the brightness temperature, your latitude, longitude range, and you can have a look at the resolution as well. Is 0.01 as we've decoded earlier. Okay, so as mentioned, usually after you read in the data, it could be cloud top temperature, or it could be a 1-0 cloud mask or things like that. You can define your own threshold. For here, I'm gonna highlight regions with clouds. So I want to highlight anything with brightness temperature lower than 240 Kelvin. So here is my threshold that I've set, and the mask I want is brightness temperature less than this particular thresholds. This is how you can convert it into the required formats here, and you can use your mask to output it, output your own data sets for these binary masks. So it will check each of the pixel itself, whether the brightness temperature is lower than this particular threshold that you have set. And we'll be able to draw along this region with residual. So here I'll let it know that it has a regular lat long grid, and I would like to highlight the region with the data that I want to fill the contour with. These are the polygons output, and I can easily put them as a geodata frame so that it will be collected together as one file, which will be able to output at the later stage. Okay, so it quickly tells you how many polygons there are. For this particular snapshot, there are actually quite a lot of polygons that has cloud top temperature lower than 240 Kelvin. You can filter out the very small polygon if you want to. So this is an optional steps. If they are small enough, you can remove that. So in the end, there are only around 3,000 significant cloud clusters. Here I mentioned about the size that I would like to ignore. So very small polygon would have been filtered from this step here to this 2.7 step. And I'm only saving the significant cloud clusters polygon into a GeoJSON in this file. So as you can see here, this is a GeoJSON data frame, and I've already dropped any small clouds polygons. So this GDF data frame would be able to save as an output GeoJSON in here. So everything I have save it into the 2025 Satellite to Aviation Met Service folder that we've created in the last script. Here you can visualize the results. As mentioned, the Matplotlib and the CuttlePy would be used for visualizing the results. I have used the Playquery projection, and this is the lat long region that I am plotting. For your image, you'll be working with the brightness temperature data file, and this is the extent of the bounding box that I'm using. And you can easily plot the polygons on top of this brightness temperature plot. I've only added the coastline without any country boundaries for easier reference. And this is where you can put the color bar. Because I'm only plotting the brightness temperature, so I'll just use the black and white color scale. And you can easily change the labels and also the titles in here. I'll also show the plots here for your easier reference. You can also save it as a PNG if you want to. It will need to download the whole coastline file. And this is the information you get. So here, the black and white is the original brightness temperature plots. And the red lines would be the polygons that I have outputted as a GeoJSON, which also being saved as a GeoJSON data frame in this whole script as well. So you can easily work with other data files that you would like to output a polygon for downstream use. It could also be used if you want to highlight overshooting tops, then you can combine the water vapor imageries in addition to this infrared channel. And whenever you can see the water imageries having a lower brightness temperature, which means it is overshooting top because the moisture being thrown higher than the infrared channel. And then you'll be able to highlight those regions as well with these scripts and red polygons if you want to. Okay. Working with the Fengyun 4B is very similar, so I'll go slightly quicker with this script so we can stay on time. Okay. Okay, so similarly, we are working with the same geostationary packages, geospatial packages, and there shouldn't be any problem to use them in the Colab free account because they are quite standardized packages that you will normally use. Great. And just double checking, we are in the correct Google Drive. And okay, right. Here we go. Similar to the Himari data, I have one sample data available for your access in my Google Drive. So if you run through my script, this is the Google Drive link that I've shared with you. And you can download this Fengyun 4B data into the 2025 Satellite to Aviation Services folder that we have created in the first script. Okay. So to make sure the file has been downloaded, I'm just going to print if the path exists. As mentioned in Alan's talk already, there is an official calibration lookup table that's been available in the file itself. So what you need to do is choose the channel that you want. They will be able to take care of the calibration itself. So this is the raw data in HDF format, and this is the calibrated version. The file path that you have downloaded already include all this information. So because we're working with the channel 13, so this is the channel 13 data. This is the temperature variable, as mentioned. So similar to the Hiramari 9 data, after you've read the data set into your Python, you still need this variable name in order to extract the information that you want to work with further on in your script. Okay, here we are. I'll quickly have a look at the data attributes after I've read in the data, double checking, and to extract the data that I want, which is the brightness temperature. They have the NA values being filled as 65535. We also need to filter those out if there exists any data of those. And here, the lookup table for the brightness temperature is given in here. These are the standardized calibration script that you can also use in other channels. Okay, so in the very detailed description given in the Chinese PDF formats, they also mentioned about how they have calculated the radiance or the brightness temperature via these calibrated values as well. So if you're using this particular script, you'll be able to get the brightness temperature after you have run this particular conversion highlighted as method 1. So after you've run these few lines, you'll be able to output a brightness temperature data sets. Because I want to use X-array, it makes selections of data as well as filtering much easier. So I've also created a data array in X-array formats for later selections of a particular brightness temperature thresholds. So it's slightly long, but then I hope you understand how it goes from the raw data HDF to the calibrated version, and then further on into the radiance or brightness temperature based on the physical conversions. So you can copy this script if you're working with other channels as well. After we have brightness temperature already in a X-array format, this part is actually the same as what we've done with the Hiramari 9 dataset. So we work with Resio to get the polygon of the cloud mask. I've tried to written it as a function. So instead of the step-by-step that you see in the Hiramari 9 script in the step 2 processing, here you will be able to fit in the whole brightness temperature X-array, and you can set your thresholds as a function variable. And here it will read in the values and pick up the cloud masks. As you can see here, with brightness temperature lower than a particular threshold. You can also make sure a particular latitude, longitude that you would like to work with, and I'll put it as a polygon. Because here it will be a set of polygon being given by the Racegeo package. I have collected them all as a geodata frame, which makes it easier for you to output and also pass on to the downstream application as well. Okay, so here, if you run through this, okay, you can see here the data shape that being read, the temperature range, as well as how many pixels are there with very cold cloud top temperature. And it also tells you how many polygons have been created based on that. Here's an example of the list of the polygon in the geodata frame. Again, if you want to, you can filter very small polygons. And for this particular snapshot here, there is a much small polygon. So there are still around 1,000 significant cloud clusters. I will save the GeoJSON in the folder as well. For your operational use, you can pass this particular GeoJSON file further on to the downstream user. Just to visualize the results, similarly, you read in the data, choose a particular lat long bounding box, and then I also overlay the polygons on top of this brightness temperature plots. Again, I've only used the coastline rather than the country lines, as well as the color bar. I just use the black and white version for cloud top temperature. So as you could see here, the red lines are all the polygons being outputted with cloud top temperature lower than 240 Kelvin. And there we go. So I think that's all from me. Thank you very much. And I'll be sharing all the scripts after the training.
Thank you, Dennis, for your presentation, especially for this particular application area. Because we have limited, we have heavily behind the schedule, so we have limited time for Q&A. So I would like to invite other presenters to check the questions in the chat and answer, if possible, in the chat. So let's move to the next topic about the Python and artificial intelligence. So
yes,
I invite
yes, it's my
Dr.
time,
Alan
right?
Tong
Yes.
once again for your closing topic. So over to you.
Yes. Okay. Thank you very much. Thank you for the previous two speaker, Alpen and also Dennis, introducing the power of Python and also the Colab environment, so we can run the script and also on some cloud service and do some quick check during the development, and it is quite deviated from the local server environment, and I also feel quite useful to do so, and especially when you are not sure whether the code is correct or not. But in this generation, maybe AI is also useful to do so, because sometimes when we want to do some function or some effects on the image, but you don't know how to write down the code in the Python language, and you don't know what's package you need to use. So AI sometimes it will give some very quite useful advice to your questions. And so actually in this topic, and I will pass my time to my assistant. Actually, she is my intern, and Miss Holly Chen, and he is a undergraduate student from the Department of Earth and Planetary Sciences, the University of Hong Kong, and she joined Hong Kong Observatory in this January, early this year. as a internship, just 1 year program. So she is ending his internship this month and next month. And actually, in the beginning, I have tasked her to do a hotspot or wildfire identification from satellite data. And actually, in the beginning, he has completely low knowledge on programming. But at the beginning, I have tasked her to decode GOES satellite data. And so you can see a lot of GOES satellite data example in the presentation later on. But actually, same concept could be applied to other satellite, for example, Himawari and also Fengyun satellite data, I think, because you just ask AI to do so. And so, in this presentation, she will show you how she interact closely with AI and just ask question to AI, and AI will provide you the Python code, and then you can use the Python code on your environment. But you cannot trust completely on AI because sometimes AI will give you something you don't want and you need to modify further. So let me pass the time to the Holly for the AI, to show the power of AI. And yes, Holly.
Thank you, Dr. Tang, for the introduction. And I hope everyone can see the screen and also can hear me. Okay, so hello everyone, I'm Holly, and I'm going to share with you all my experience on how to use AI to assist in my daily tasks during my internship in HKO, and also learn how to code, how to write Python codes. So let's get started. Okay, so these are the coding platforms I use during my internship. Normally I use Visual Studio Code, but in this workshop, all the codes are executed on Colab, and the images are saved and presented to you in this PowerPoint. And all the scripts are from AI. So the type of AI I used in the project is a general large language model Grok. During my internship, I have used several free AI models, including PoE Assistant, Gemini in Colab itself, or Microsoft Copilot. But in my personal view, I think Grok is the best AI model in understanding the scientific recipe and documents, and also providing me a very functional scripts. And also, I use general large language model image for coding specific AI is because sometimes the documents are in foreign languages, such as Chinese, or I've even seen Korean documents, and language model can help translate these documents and assist in my AI coding. And so how AI helps me in writing Python codes? AI already have comprehensive knowledge of libraries, including packages and submodels we need for our coding in image generation. And therefore, we do not need to memorize all the stuff, all the knowledge, all the packages, or how to write the commands like the brackets or the formats. All these kind of issues can be solved by AI. And also AI can quickly sense the syntax error in the AI in the Python script, and be able to give me several alternative suggestions to improve the processing, the image processing. Okay, so my target is to convert from raw ANSI data into our final product, the images. First of all, the raw ANSI. ANSI file is a very common type of file to store multi-dimensional data, which is very suitable for satellite data. And my raw ANSI is from GOES 18 satellites located right above 137 west degree longitude. But I'm pretty sure all the coming up contents are transferable skills to other satellites as well. Oh, sorry. Can you hear me now?
Yes, pretty clear here.
Okay, thank you. So let's continue. And below here is a sample file I opened in Panoply. I encourage all the beginners, for people new to satellite data, to open the raw ANSI in Panoply first, because this gives you a general concept on how the data works. And also, if the AI do not know what you're doing, you can feed the metadata here to AI, such that we can teach AI what we are going to do. So after downloading the raw ANSI file into our computer, we need to read the raw ANSI files. We can either have a very simple view on Panoply, or we are going to write a Python script to decode the raw ANSI file. So I just give this question here to Grook. I simply say script to read all the metadata in the file. And also I provide a full path for AI, because sometimes it is very crucial for AI to provide a functional script, because we need to know where the files are saved and where we are going to output our data. And here is, on the left hand side, is part of the script generated by AI. Sorry, can everyone hear me now?
There is some kind of echo on your side. I think you are too close to the microphone. You should a little bit make it a bit distant. Yeah, you are too close to the microphone, and therefore there is a bit of echo when you are speaking.
Okay. Sorry, testing.
No, it's too low, too far now. Can you try a bit of a middle?
Or now?
Yeah, that's
So-
fine. Now I think it's fine.
Okay,
Just speak
thanks.
up. Yeah, that's fine. But
Okay, thank you. So this is the part of the script that AI generated to me.
sorry, Holly. Now it's too low. Sorry for that. A little bit. Then you should speak a bit.
Okay, testing. Sorry. Testing.
No, that's fine. That's fine. Yeah.
Okay, thank you very much. Let's continue. So here, the script also write dimensions and also variables for me to decode the metadata, which is a very important information for my communication with AI, because it is very hard to describe what is inside the raw ANSI file. But with metadata, AI knows very well what is stored inside, and very comprehensive data. But at the same time, I also want to know why AI can generate a very perfect script for me. So I asked a follow-up question: why do you know the metadata are inside the raw ANSI file? And this is the exact wording that AI answered me. Is because every single GhostNet CDF file had followed the exact same template. Therefore, we can see AI do actually have a prior knowledge to how raw ANSI look like, and we do not need to further pay many efforts into it. Then we can get what we want. Okay, so after reading the ANSI, we do the processing, which is the part covered by Dr. Tang in his presentation previously. So I'm going to skip this part. This is the ANSI file, the converted ANSI file into physical variables with latitudes and longitudes. And now we are ready for generating satellite images. Satellite images are generated by combinations of channels, and I'm going to show you guys 4 different products, including a single channel file down here. The infrared image, and then the second one is the HKO version of the convection image that requires operations between 2 channels, and then we have 2 other RGB images, including fire temperature RGB and metro true color RGB. This is a summary of my common Python packages used during my internship, including NumPy for mathematical operations. You can see in the script some like np.clip that is for the setting upper and lower limit of the data values. And then we also have np.sqrt, which stands for square root. And these are some common examples of how NumPy help in mathematical operations. And then second one, we have xarray to handle multi-dimensional NC files. And then we have matplotlib to create plots for titles, legends, essays, etc. And lastly, we have Cartopy for particularly for map generation. And this is this extra reference package I also used in an extra part that I hope I'm going to show you. Okay. So the first product is the RR1 image, and I'm going to focus on how to use AI to help me change the projection of the images. First of all, I ask AI, I give AI what I have, that is the physical variable with latitude and longitude NC file. And this is the metadata. I simply copy and paste it to the group chat. And I also provide what I want, including the color bar range, 180 to 310 Kelvin brightness temperature, and then white for 180 and black for 310 in grayscale, so that AI knows how my image should look like. And then AI responded me with a full script, including five sections. The first one is to import packages we need, and then the second one is to define the color map. The third one is the image coloring, where calculations happen here, and brightness temperature is calculated into a 0 to 255 color value, and then we set RGB into R equals to G equals to B, such that the image would be in grayscale. And the fourth part would be the input and output file paths. And last but not least, the plot compositions, including the title, the axis, the color bar, etc. So follow-up, I want to change the projection of my image. So I asked the follow-up question to study the script AI just provided me, and then give me through this infrared image script under different projections with Cartopy. These are the six images AI provided, but this is not ideal because we see a large empty space here, and therefore I want to rotate my image a little bit to center at where my satellite located. So I asked follow-up questions. First, I want to know what AI have in its understanding. So I asked AI to provide all Cartopy projections and see if we are on the same page. And then I also asked AI to explain each of the projections so that I can verify its accuracy and also to learn at the same time. Besides, I also asked whether we can choose the center level of each plot into the satellite nadir. So here's the exact answer AI provided, including 23 projections in total. But 23 is a bit too much, so I asked AI to choose suitable ones. For my satellite here, GOES 18, and then set the center of the photos to the nadir. And for consistency, I also defined the coastlines into cyan color. And you can see here, this column, sometimes AI might give a pretty creative answer, but it's functionable, so I'm okay with that. And then next up, we have the AI provided image. It is in black background color, and also the color bar is reversed. It's an inverse direction, which is very not ideal, and also latitudes and longitudes without labels. So these are the issues we have if we only trust AI. So this is when human power come in. For easier and simple corrections, we do manual corrections to avoid confusion during our conversation with AI. We modify the color ourselves. We define the color again, and then we define the satellite information, which I will show you in the next slide. And I also ask for complicated question. I ask follow-up questions to AI to help me to deal with the grid lines. Here's the sample, and the gray commands are the old AI commands, and the new one is the corrected version. So here on the left upper corner, you can see the reason why our color bar is reversed. So it's very simple. We just put black and white in a reverse order. And also I want a vertical color bar, and therefore I change it to vertical. And here's some satellite parameters that do not align with our desire or the documents told us about. This is the AI knowledge, and this is the official documents. So I change it a little bit as well. And for follow-up AI correction, in the old image, AI defined a standard extent of the image, but this is not ideal. I want it to be more flexible and read the maximum and minimum data from NC file. So here's what AI returns me. It is very complicated. I don't think beginners with Python can write this very easily, but with AI, this is possible. This is the 5 projections AI suggested, and you can see the latitude and longitude read from the NC as well. So now moving on, I want to see a cropped version of image. So I just tell AI, I want a cropped area script with latitude and longitude defined here, and also suggest a suitable projection for me. Then AI do all the stuff and then provide me with the exact same ideal boundaries and also the projection we need for this boundary. To follow up, I asked AI to give me a variety of areas with variety of projections as well to explore different latitudes, such as here we can see Alaska in the very higher latitude, and AI can do the correct thing to suggest a polar specific projection for me as well. But the limitations is that AI can do wrong stuff or creative stuff, for example, suggesting an area out of the valid GOSI 18 satellite range. So I just I redefine the area for AI here by repeating myself, and this is how I communicate with AI. Moving on to the next product is the HKO version of Deep Confession Image. Here is the HKO color palette for Deep Confession Image. And this is where human power come in, because AI do not know what is meant by deep confession image. So we define the color bar and also the brightness temperature range here. We also tell the AI how we operate between 2 different channels by subtracting between brightness temperature in channel 13 and channel 8 to get our product. AI is also very powerful to fix and explain very minor issues. For example, here in the old product, the color bar tick labels is a bit shifted, misaligned with what I want. So I ask AI suggest why the text misaligned with the color changes and fix the issue. So AI explained to me that because the old color bar is using evenly spaced points that might misalign with my color change. And then for now, the new solution is to define the boundaries exactly at where I want. So you can see here and here, the misalignment is fixed. Moving on, we have RGB images. And so sometimes AI do not work perfectly, and it is very important for us to do our online research as well. So for consistency, I ask AI to study the IR image script we used and then change it into an RGB script. And I copy and paste the fire temperature RGB recipe online from official document here, and AI decode and then provide me with the script. However, it looks very red, and this is very different from what we see in the recipe documents. So we know that it is wrong. And now we are going to try to find out why and fix the problem. I do some online research and find this sample script from this link, and this works pretty well online, and I feed this sample script to AI and ask AI to understand the logic of the sample script and compare with my previous script and suggest why the coloring is incorrect. And turns out that because AI understands the definition of gamma correction wrongly in the previous script, the origin recipe suggests 0.4 gamma correction, but in fact it should be 1/0.4. This is how AI understand gamma correction, this term, wrongly. So here we fix the problem, and then we also fix the clipping problem such that we get a very nice fire temperature RGB image. We do similar things for natural true color image as well, and the sample script is also from this link. I also do the same job, just feed AI with the sample script and return with this image. Here we show a side-by-side comparison of the two RGB images, and this is done by AI as well. I just tell AI I want a side-by-side comparison because for example, this occasions I want to show you the smoke plume as well as the hotspot locations. Then we can ask AI to fix the problem. Next up, I overlapped the two RGB images with each setting to transparency 50%. This is also done by AI, and I have included a group conversation, which if there is time, I can show you all how to do it. And please be reminded that in this PowerPoint slide, it is a very simplified conversation, the question and answer progress with AI. The reality is that multiple of errors is jumped up when I execute the code on Colab, but there's no need to panic or to worry. We just copy the errors and AI can help us debug and explain the errors if we do not understand what the errors is talking about. So in this last part, I'll show you the sun glints problem I encountered during my internship, and all the algorithm behind is done by AI as well. This is the Skyfield package used to find the subsolar point, and here is a Hilberstein formula that's suggested by AI as well to calculate the distance between 2 points on a globe surface. And then we do our background image in natural true color image as well. But the background information is that I do a lot of research beforehand to understand, to give a guess of what is happening. And at the end, I come up with the idea that here is a satellite and here is a subsolar point. The midpoint would be a perfect spot for reflection to happen, and therefore a circular region around the point would be a very bright area that sun glints problem happen. Here we can see the raw image and the sun glints diffusion problem happens here, and this is what AI helped me to identify the area such that I can understand more about the image. So to summarize, here's some tips for us to communicate with AI. So how to ask AI questions. First of all, be specific of what you want to achieve, and then you be as detailed as possible to give AI your request. to prevent AI being too creative and do all the stuff itself. And also for very complicated tasks, you just split up your tasks and make sure your steps and AI steps are aligned. So lastly, how to listen to AI. AI do help us a lot, but we do need to pay the effort as well to grasp the logic behind the script and ensure it aligns with what we're doing. And then we can be open-minded to alternative solutions that AI suggests us, and also understanding the error messages and get familiarized with common error messages would be very helpful for improving the efficiency, such as you see if the error is you haven't installed a specific package, then you know how you need to install before you run the script again. And then be patient, because the communication process would be complicated with multiple questions and answers needed. And last but not least, AI answers are not guaranteed to be the same every time you ask the question. If you want to be consistent with what you're doing before, then you can copy and paste your script and serve as a sample script for the AI. And so we can see in this PowerPoint that AI is easy to use and a very powerful tool for people with no prior knowledge in Python to be able to carry out satellite image generation tasks and learn how to code. But there is also limitations, and we do need manual corrections in the meantime. That's all for this part.
Okay,
Yes.
Holly, so thank you very much. Actually, this PowerPoint is showing the simplified version, and just the communication. She is asking actually in various slides, she just asked AI to do something, and then the code, the Python code is generated by AI. And then Holly, in the working environment, he copied the code and from the AI generate the AI result to the local server, for example, the Visual Studio Code on local computer, or also the Google Colab situation. So actually, the working environment is similar to the previous two speakers, but what Holly present is the methodology, is the how to ask AI. And previously, for example, when I do Python during my undergraduate, I just grab a lot of template from internet and then to learn the spirit behind, and then to transform into some code I can use and to generate something I want. But now currently AI will do this part for you, and you just write a sentence, normal layman sentence to ask AI, I need this thing. And then AI will generate the Python code, and then you just copy and paste to your working environment. But it is a simplified version. But maybe Holly, you can also show the PDF showing the chat room, the exact conversation you communicate with AI, and show how error happened during the conversation, and then how you rectify AI and to fit your purpose. And because we still have time, maybe just a few minutes to show the actual situation, and it is more realistic than the PowerPoint presentation. Maybe Holly, can you share?
Hello everyone, can you see my screen now?
Yes, I can see the PDF right now.
So on the left hand side here is the PDF, is the exact conversation I do with Brooke. Highlighted in yellow is my question to Brooke. So give you some background information first. So we have already done to create the script for generating the true color RGB image and also the fire temperature RGB image. So I just feed AI with these two scripts here, all the way down here. Okay. So this highlighted in blue is the answer from AI. So AI provided me a script that I want to do a side-by-side comparison. Here's is the product I generate. I copy and paste the Python code here and then put on Colab, and then Colab return me these two images. So we do a side-by-side comparison. It looks pretty well, but then the title is not ideal for what I want. And then so I ask follow-up questions to specify what I want in the title, and AI return me another script, and then I run another script on Colab. And okay, so next up, I don't want a very large spacing in the title here, and therefore I give AI a subtitle of what the format, what I want in 2 lines separated. So AI generate a script with the fixed problem, but at the same time, during the processing of the script, Colab returns me with these error message, and I copy these error messages into AI, the Grok chat room here, highlighted in green. Simply copy and paste. You don't need to understand what is inside, what it's talking about. Then you ask the question, why invalid and what happened? Then AI explain to you, this happens because we did not deal with the negative reflectance values. And therefore, I ask AI to fix it for me again. And this is what AI gave me. We can see the format is slightly distorted. And I also asked in the chat that I want a overlapped image as well. AI provided me with this, but the format is again not very ideal. So sorry. Okay, so I want to fix this image in particular, and then I only need the full script for this product, and therefore I specify my question again to narrow down our issues, because too many issues, then AI is a little bit confused of what we want to do, and then we make sure the title format is similar to perhaps previously I feed AI with another script that is perfect for me, and at last AI returns me with this image. This is perfect for me with a pretty well title, including the daytime and then the region, and then this is an overlapped image of the 2 RGB images with correct labeling of latitudes and longitudes, and then the transparency. And you can see the composition is a little bit complicated, but at the end I can achieve what I want to do. Thank you.
So thank you, Holly. And yes, and that's also answer my the chat room question. You can see how you need to interact closely with AI and also provide further information and to fix the technical context, for example, the script and code, because when you provide more information, then AI will understand more what exactly you want. So here AI will give a script closer than closer to your expectation. And yes, I think it's quite enough for the parts. But don't worry, although the script is the font size is small in the presentation, the PDF is long at over 20 pages for this chat room, just like you're looking at some chat WhatsApp chat record, for example. But don't worry, we will share the information to you then. And also, actually, the script, the Python script presented here is not important because, as I said, and what you need to do is to ask AI to do so. Even you don't, even the font size is too small and you cannot check the code, actually you just type the question on the Grok, and then he will generate the rest for you. And also, but the most important thing is you just use the simple platform and just Grok or other AI platform on. You just need the internet connection with the internet, and then you have the accounts. You just type some sentence to ask, and then he will generate the rest for you. And the technical barrier is not very high than the last decade. Maybe in this AI generation in this year, or just few years, starting from few years ago, the barrier is lower than the previous experience in last decade or 20 years ago. And that's all for my part. I think I can pass my time to Yongqing, and thank you very much.
Thank you, Holly and Aaron, for your very interesting presentation for these areas. I think we have 5 minutes. I also once again ask my colleagues, Julia, to put the questions we collected on the screen. Most of them are answered. I just want to check with the presenters, Aaron, Apple, if you want to give some explanation to the questions. So first, start from Julia. Could you put the answer the question on the screen? So first to Aaron. Do you want to give a little bit of explanation, or just so Aaron, up to you.
Yes, for which question? Sorry. Actually, I have some further for the Himalayan 8 or 9 data. And yes, previously I mentioned that JME is not providing the data in NZ file, but as one audience just informed me in a private chat room that actually you can download the data processed by JAXA rather than JMA. JMA and JAXA is different organization, but JAXA also from Japan, and they have the data from JMA, the Himalayan 8 and 9, maybe from DAT format, and they have processes the data into a NZ file, and then if you want the data provided from JAXA, and actually you can register in this link. Actually, I just browsed this link, and they are also providing some other observational data, for example, the aerosol or sea temperature, I remember correctly. Then yes, it is also one of further information you may find useful. And yes, I don't think I have other things to say for other questions because it has been explained. But I see from the latest chat room that someone is asking any recommendation on the specific AI tools, and for example, the Grok or ChatGPT. Actually, Holly is demonstrating with the Grok, and I think Holly can say something about this because you just told me that you have tried various tools, for example, Grok, ChatGPT, and other tools, and you feel that Grok is the most the suitable one at this stage. Is this it? Holly, can you can say some words on this?
Sure. So during my internship experience, I first used POE ChatGPT, but then the script is not very specific. Sometimes I tell AI the input or output paths, but ChatGPT simply do not know what I'm doing and cannot provide me a functionable script. Then I start to use Grok. Grok for me is doing a pretty well job. It returns me a full script from import packages to the last part to output the file pretty accurately. And for Microsoft Copilot or the AI in Colab itself, I think they can provide you a small sections of script each time, but then for beginners in Python coding, a full script would be more helpful, I think. So I chose Brook basically in my operation.
Okay, thank you, Holly. And so on same page, and some are asking the environment of to run the code. I think is just answer the question. Maybe it actually for during the project, actually she run on the Visual Studio Code on local computer, or for demonstration, she can also use the Google Colab, similar to the previous two speakers. So actually, the code is generated from AI, but the rest, how to run, how to execute the code is same, and you need the Python environment as well. Yeah, that's all for me. Thank you.
Thank you. So we're back to Apple. The question to Apple, Julie. So, Apple, do you want to say something about? Okay, thank you.
Okay, basically I have already answered in the chat box. For the answer, yeah, so satellite packets only text file with the specific. Yes, actually yes. Currently just support for the satellite data. But in the my plan, I will improve the capability for these packets, like OpenU for the GK2A and Fengyun for A and B in the next version satellite package. And the next question, can you do real time? Yeah. And for the YouTube, for specific Python, yeah, I don't have specific video for Python. But for the feature, I will upload for the satellite packets specifically to make easier for user. And for question from Afghanistan, yeah, in this case, we need to using limitation resource. You can use just your laptop or your PC. Just download every 10 minutes. The file, the size of file just less than 4 megabyte. I think it's good for the limitation connection. And using the satellite Python package, I think for the basic product in satellite, just using for a line, and you can get the image satellite images immediately. And I will reply your email. I think I have new email from Afghanistan College. Okay, I think that's all from me.
Thank you, Apple. Is there any question to Dennis? No. So, thank you for all presenters. Let's give a virtual applause to all the speakers from HKO and the BMKG. Your experts, patient, and practice insight have made this workshop a success. I believe each participant leaves with the knowledge and the tools to apply in their work. once again, thank you for your participants, for your patience for 3 hours. Also, some participants also asked for the similar workshops for in the future. Maybe we were working with our colleagues and partners to think about the future further training for this kind of tools. Also, I would like to thank my colleagues in Geneva, Zua, in early morning to support this workshop, and my colleague Julia to assist us to organize this workshop. So I would like to conclude this virtual workshop. Have a wonderful day and the best luck on your Python and satellite data journey. Bye-bye.